The circuit diagram below, the battery has got negligible resistance, internal resistance, which is cool because that makes it a bit easier. With the switch open, so in other words, this part of the circuit actually doesn't exist at all. Determine the reading on the ammeter, ammeter number 1, and the voltmeter, which is across the 6 ohm resistor. So it's actually really quite simple, this. So current strength is equal to potential difference divided by resistance. The potential difference of the whole circuit is 12. There's no internal resistance, so we don't have to worry about lost volts. And then you've got resistance, which is going to be the 6 ohm plus the 2 ohm, which means that you've got 8. And you land up with 1,5 amps over that whole circuit. The next thing that's going to happen is they're going to ask me what is the reading on the voltmeter. The voltmeter is connected only across the 6 ohm resistor, so V is equal to I times R, and I land up with the current on the main branch, because there is only a main branch here, there's not even a parallel network, multiplied by the resistance of 6, and I land up with 9 volts. Now things change. I land up with the switch is now closed. The ammeter reading will change and the voltmeter reading will change because it's a distribution of energy over the different resistors in the whole circuit. So you can't just start grabbing your 1,5 that you calculated earlier. So we now do have a parallel network to the circuit. So if the reading on A1, all that I know is it's 3 times A2. So what's going to happen now is I'm going to say this is 3 times A2. 1 A2 goes there, meaning that 2 A2s have to go there, which means that I am now in a position to say if 2 A2s go here, what is the new potential difference on that voltmeter? The voltmeter is going to be 6 times 2 A2, which is equal to 12 A2s. That's the voltmeter reading over there. And if I now look, I've used this branch. Now if I look at this branch over here, what have I got? I can say V is equal to I times R, but I'm actually interested in the resistance, so let's go R is equal to V divided by I, and V is equal to, it's the same voltmeter between blue and green, and therefore I'm going to land up with 12A2 divided by the current going through there, which I know is 1A2. A2's cancel, and therefore my resistance is equal to 12 ohms. If you wanted to, you could have made an assumption. Let's say you had started with the word assume. A1 is equal to 1,5 amps because you did that earlier. And that would have meant this is 0,5 and this is 1,5. 1. You would have landed up with the right answer, but you needed to say that you were making an assumption because it is not actually true at all in this particular circumstance on account of the fact that this whole parallel network actually changed the circumstance of what you had calculated over there. Now we've got 3 electrical devices, X, Y, and Z. They are connected to a 24 volt battery. It does have an internal resistance that's been put in. As shown, the power rating of each of the devices is given. So they've basically said to you, this square does not mean a resistor specifically. It means a device. It might have some resistance, but it's not a resistor. Or could be, but the point is that these are devices, X and Y, on the diagram. With the switch closed, only switch 1, let's see what happens. So I've done the colors over here, and it first says calculate the current through device X, so let's look at that information. I know that power is equal to potential difference times by current, and potential difference is 20. Power, they've told me, is 100 watts. What is the current going to be? The current is going to be 5 amps. The next thing they ask me is what is the resistance of device Y? And I need to consider that device Y is going to have a power of 150 watts, and I don't really have very much more information, but do I or don't I? Let's think for a second. What if I connected a voltmeter across here? That voltmeter would have been between pink and green, which means that this is 20 volts. So it doesn't matter which branch I'm on, I'm going to have a potential difference of 20 volts. So I can now say power is equal to V squared over R. Power is 154. Why? V squared is 20 squared, and the resistance is what I'm going to calculate, and I find my resistance turns out to be 2,67 ohms. Calculate the internal resistance now of the battery. So I'm able to say, well, I can work out how much current is on this branch over here by saying something along the lines of power is equal to V times I. I know it's 150. I know the potential difference 20, and therefore the current is going to be equal to 7,5 amps. So if I've got 7,5 on this branch and I've got 5 on this branch, the ammeter up here is reading 12,5 amps. So I can say that the lost volts, I also know between pink and green, I know that I've got 20 volts. So my lost volts is 4 volts. It's 24 minus 20, which is equal to 4 volts. And then I'm able to say internal resistance is equal to however many volts I've lost divided by the series current, and my lost volts is 4, and my series current is 12,5, and therefore I land up with 0,32 ohms. Now I'm going to close the switch, and it says if you close that switch, the electrical devices still function as rated and their resistances are unchanged. In other words, nothing changes when I stick this thing in. What type of a device, if I put it into the circuit, would make no difference at all if I added it in? Well, what if it was a voltmeter? Voltmeters have got very high resistance, and therefore no current flows through them, and they make no difference whatsoever to the circuit. Very high resistance, therefore almost zero current. Therefore no difference. And some people wrote a passive observer. Ammeter A in the circuit is shown. It has negligible resistance and reads 0,2 amps. The battery has an EMF of 4 volts and a total resistance of 2 ohms. So now, if I want to get a voltmeter across here, voltmeter is equal to I times R. The series current is 0,2, the resistance is 6, and I land up with 1,2 volts. Show that the potential difference across the parallel combination is going to be 2,4 volts. Well, let's take a look. If I were to say, how much lost volts did we have altogether? Let's say lost volts is equal to series current multiplied by internal resistance, 0,2 multiplied by 2, and I land up with 0,4 volts. So I have got EMF is equal to internal resistance plus the resistance across the 6 ohm resistor plus the resistance across the parallel network. 4 is equal to 0,4 plus 1,2 that I've just worked out, plus the resistance across the parallel network. And the resistance across the parallel network turns out to be 2,4. There's no mark for 2,4. They told you 2,4. You need to show me how you got there. Now it says find the effective resistance of the parallel combination. R parallel is equal to V over the parallel branch divided by current over the parallel branch. So the, this isn't R, this is the V of, sorry. So the voltage is 2,4 across the parallel network. And remember, this entire current of 0,2 goes into the parallel network. Even though it splits, it's all there, and that means that I land up with 12 ohms. Now it says, what is the resistance of just this top branch over here? Well, I know that 1 over R parallel is equal to 1 over branch 1, which is 12 plus 18, plus 1 over x plus y, which, by the way, is called Mn, which is what we're trying to find. So it's 1 over 12 is equal to 1 over 30 plus 1 over the resistance of Mn. And when I plug that all into my calculator, the resistance of Mn turns out to be 20 ohms. You can actually just plug it into your calculator. 1 over 12 minus 1 over 30 inverted, and you get 20. And finally, what is the resistance of Y if a voltmeter across X reads 0,4? Well, I know that that means that the potential difference across Y is equal to the whole parallel network, 2,4, minus 0,4. That's equal to 2 volts. Then I know that the current on this branch is equal to the potential difference across the parallel network divided by, first let me try, we know it's 20 ohms of resistance, so I can divide that by 20 ohms of resistance and land up with 0,12 of current. Now I'm going to say the resistance of Y is equal to the potential difference across Y, which I've just worked out is 2, divided by the current going through Y, which I've worked out is 0,12. And I land up with 16,67 ohms. The circuit shown consists of an array of resistors connected to a 32 volt battery of negligible internal resistance. The resistor marked R is variable and can be anything from 0 to infinity. The variable resistor R is set so that the battery supplies the array at a rate of 80 watts. So all of these resistors are getting 80 watts. Calculate the potential difference across the 7 ohm resistor. So the first thing I'm going to do is I'm going to say that power is equal to V times I, which is equal to, 80 is equal to 32 times current, and current turns out to be 2,5 amps. So that's on the main branch. Now I'd like to know what is a voltmeter reading across there. So I go V is equal to I times R, which is equal to 2,5 multiplied by 7, and I land up with 17,5 volts. There's no internal resistance, so it's reasonable for me to say that that is 14,5 volts across the parallel network. Now it says, what is the value of R? Well, V parallel, as I've just said to you, is equal to the full 32 minus 17,5, and that's 14,5 volts. Then I can say that R parallel is equal to the whole of V parallel divided by the current going through the whole parallel network, so that's 14,5, and the 2,5 goes through the whole parallel network, so it's 2,5, and I land up with 5,8 ohms of the entire network. Now I can say 1 over R parallel is equal to 1 over 20 plus 1 over r plus 1 over 10. And this isn't r parallel, it's 5,8 because I just worked it out. And when I plug that into my calculator, r turns out to be equal to 44,6 ohms.